Hey, welcome back, everybody. It's time for Mega Calc 2 integral number 3. This integral features substitutions, clever algebra, partial fraction decomposition, and the arctangent function. This is a fun journey. I hope you enjoy. I think this is quite a blast. So let's go on an adventure. Okay, so here is our integral. And so we're actually going to start off with a substitution. We're going to let u equal this. And then our goal will be to get rid of this, write it in terms of u, get rid of this, write it in terms of u. So here we go. We're going to let u equal the square root of x. And so that means that u squared is equal to x. Okay, so I'm happy about that. Let's try to write this in terms of u. So let's square both sides. And then it looks like we should add 1. Okay, so I'm happy about this, happy about this, because I can replace both of these. I want to replace this, and so I'm going to use this to replace the dx. So if x is equal to u squared, well then dx is exactly 2u du. And so now we can replace everything. We can write it in terms of our new substitution variable u. All right, so dx, what would we say? Okay, so right here, so dx is exactly 2u du. Radical x, that's exactly u. And then x squared plus 1, we're going to call that u to the 4th plus 1. The u's will cancel. And I think I'm going to write the du to the right, although you don't have to. Okay, so that seems fine so far. This is where we're going to start being clever because there's not much we can do at this point. So I'm going to star this. So we're being clever here. So we're going to think of 2 as 1 plus 1. So in that way, we can write this as u squared plus 1 minus u squared plus 1. The u squares, I mean, they will cancel. That's 0. 1 plus 1 is 2. So I've done nothing illegal. And we're going to see in a little bit that that'll be very useful for our substitution. Okay, so the next thing I want to do is maybe factor out this negative and break up my fractions. So I'm going to break up my fractions as this quantity over this. So that seems pretty good. And then minus, so I will be factoring. So that's this quantity if I factor out a negative 1 over u to the 4th plus 1. So just sort of common denominators in reverse. Instead of putting two fractions together, I just split them apart. And I'm probably going to split these into two separate integrals. Give myself a little room for du because there's a bit of algebra that I want to do in just a moment. Well, here we're going to be clever again. So the piece of algebra that we need that's going to lead us towards a substitution, although maybe not clear right now, is 1 over u squared over itself. That's going to sort of lead us in the direction we want to go. We did something similar with the last two Mega Calc 2 integrals, part 1 and part 2. We did that with the 1 over cosine squared of x. Same idea. And so now we're just going to distribute and sort of clean that up. So let's see what happens here. All right, so distributing. So this times this is 1. This is going to be 1 over u squared. I'm just going to write it like this. right? That is 1 over u squared. So yeah, just essentially distributing, no problem there. Same thing downstairs, I can distribute. That'll give me u squared plus u to the minus 2 when I distribute and clean it up, du. So yeah, same thing here. So again, we're going to go ahead and just distribute. And so it looks like 1 minus u to the minus 2. And then downstairs distribute as well. Okay, so this is promising so far. And we essentially want to do some algebra that's going to lead us towards a substitution. So it's going to be a bit tricky. So maybe I'll star this part. So maybe I'll block this part off. And we'll call this maybe tricky algebra. It's worth doing problems with tricky algebra and trig because the more tricks you're exposed to, the more tools you'll have in your problem-solving handbag. So you want to solve as many as you can. Okay, so I'm going to have a section that's sort of corresponding to this and another section corresponding to this. So maybe I'll reference this as like star, and this one is double star. Okay, so for star, we need to make an observation about this quantity, and that'll actually be pretty helpful. So I'm going to say, well, since u squared plus u to the negative 2 can be thought of like this, so u squared minus 2 plus u to the minus 2 plus 2, this will be useful because I'll be able to factor this. I mean, what we have here is a nice perfect square trinomial. Then this will factor nicely into u minus u to the minus 1 quantity squared plus 2. Right, you could factor that into 2 parentheses, but they would both look like this. Well, since this is equal to this, I want to consider this quantity to be my substitution variable. So I'm going to say we should let z be equal to u minus u to the minus 1. And if that's the case, so now you get to see why we want to let z equal this. Because watch what happens when I take the derivative. dz is equal to 1 plus u to the minus 2 du. So this particular choice of z is good because its derivative gets rid of all of this. Right, so that's quite a nice choice of substitution variable. Okay, so we can get rid of this. Now we have to think about what do we have to do to get rid of this? Well, I think if we're careful, since we know what z is, we just sort of have to follow this out. So let's note that u squared plus u to the minus 2 is equal to, so just following this, that's z squared plus 2. Okay, so yeah, it should make sense. I mean, we're letting z equal this quantity, so every time I see this quantity, I can call it z. So that'll be z squared plus 2. It's useful because I can replace this, right? I can call this z squared plus 2. So that's handy. I'm able to replace this, and I'm able to replace this. So let's see if we can do something sort of similar for this over here. Okay, so double star. Same sort of thinking. So for double star, let's sort of partition this off a little bit. I'm going to say, well, since u squared plus u to the minus 2 is equal to u squared plus 2 plus u to the minus 2 minus 2. I mean, that's true. I've just added 0, but this is a useful form of 0 because this is now a perfect square trinomial. So that'll factor nicely into u plus u to the minus 1 quantity squared, and then there's that minus 2. So very similar thinking. Okay, so we're gonna how about y? So let y equal this, and we're gonna get confirmation that that's a good choice for substitution variable when we take the derivative, because dy, well, what is dy? dy is exactly 1 minus u to the minus 2 du. So that confirms my choice of y. And let's also note, just like we did before, so just following this, that this, which we want to replace, so u squared plus u to the minus 2 is equal to, so just follow this, that's y squared minus 2. So that's nice. I'm able to replace this with this, and I'm able to replace this with this. That's what you're going to see in the next step. So this will be replaced by this. This will be replaced with this. This portion gets replaced by dy. And then this portion gets replaced by this. Okay. Okay, so that should look a lot nicer when we do that. We should be in familiar Calc 2 territory. Okay, so we've got, looks like dz we said, right? Over z squared plus 2. Okay, so minus the integral, we've got a dy over y squared minus 2. So I'm feeling pretty good about that, and hopefully you are as well. So think about techniques of integration. So this looks like it's in an arctangent form. Maybe we'll just recall. Okay, so this is playing the role of, again, the order could be switched, of course, right? So this is playing the role of a squared because it's the constant. A goes with the constant. This is playing the role of x squared. So I'm happy about that. This is going to take some partial fraction decomposition. So I'm going to put this on hold. And so let's do the partial fraction decomposition for this. So we've got 1 over y squared minus 2. But I could actually factor that as if it were the difference of squares. So I can factor this into conjugates, right? So this is going to be, it looks like, I don't know, how about minus y minus the square root of 2 times y plus the square root of 2. So yeah, really how I would factor the difference of squares, but just realizing that it works on more than just perfect squares. But in terms of partial fraction decomp, when I classify the factors here in the denominator, this is linear and unique. So I decomp it with a constant. So a constant over the first factor plus a constant over the second factor. That's how we decomp linear unique factors. Okay, so I'm really dealing with this part here. And so maybe I'll separate that just for some more room. So that's equal to a, again, a over the first factor, we said, plus b over the second. So now I've got more room. And so let's multiply everything by the this right here. So this is y minus radical 2 over y plus radical 2. Okay, so what is that? The least common multiple of all the denominators. So we're going to distribute through and then just cancel where we can. So this over this would leave me a 1. Now here, so this would cancel with this, and I'd have a times this left over. Now here, this would cancel with this, and I'd have b times this left over. Okay, so now, so you have to realize this equation is true for all values of y. So that means we can choose convenient y's. So for example, if I chose y to be the square root of 2, this term would drop out, and that would allow me to solve for a. So I'm going to say, okay, well, if y was equal to the square root of 2, plug that in for every y, I would have y is equal to a times square root of 2 plus square root of 2. And so that means that 1 is equal to 2 radical 2a. And so a is equal to 1 over 2 radical 2. You can rationalize if you want, you don't have to. Okay, so similarly, if I wanted this to drop out and I wanted to solve for b, you just say, okay, what choice of y would make this drop out? Well, if y is equal to minus radical 2, we get the following. So this will be 1 is equal to, so this is minus radical 2 minus radical 2. So that's minus 2 radical 2b. And so b is equal to minus 1 over 2 radical 2. So in this way, we're able to decompose this. We're able to write this into the sum of little bite-sized, easier fractions. Okay, so what you're going to see me do on the next page is I'm just going to rewrite this for now, and then I'm going to rewrite this in terms of the decomposition. So this is going to get replaced by this. So goodbye this. You're going to see a over this, b over this. Okay, so what does that look like? Okay, and so dz over z squared minus 2 minus dy over y squared minus 2 is equal to, so as I mentioned before, the dz over z squared plus 2 integral, I'm going to leave that alone just for a moment, minus, now keep in mind this will affect everything. Okay, so this is going to get replaced by what we got in the decomposition. So we had a over y minus radical 2, but a was exactly this. So a over this over this. Okay, don't let that bother you. It's just a constant we can pull out in a moment anyway. So yeah, no worries there. And then we've got b, but remember b, this was minus, wasn't it? So instead of being plus b, because that's minus, it's going to be minus 1 over 2 radical 2 over y plus radical 2. That, of course, should be a radical. And this is going to be, looks like dy. Okay, so I think we're doing pretty well. So we said this was in an arctan form. So this is 1 over a times the arctangent of z over a. And then minus here. So if you want to distribute the minus, now's a good time. So this will be minus 1 over 2 radical 2 times the natural log of absolute y minus radical 2. Now we're distributing the minus, so that'll be plus 1 over 2 radical 2 times the natural log of absolute y plus radical 2 plus c. But we've got some back subbing to do. So now we have to really remember, right? We have to go back and we have to see, well, what was z equal to? And so let's see here. What was z equal to? I think it was u minus u to the minus 1. There we go. Yeah, okay. Okay, good. So yeah, let's back sub in z and y. So we've got 1 over radical 2. We've got the arctangent of, okay, so z, that's z, over radical 2. And now y, so I think y was equal to u plus u to the minus 1. Okay, so that's y, plugging y in. And now we have to remember what u was. So we've got to go way, way, way back, right? Way back. So what was u equal to? Well, I think we said that u was equal to the square root of x. So in the very, very beginning, we said u was equal to the square root of x. Okay, so of course you could bring the radical 2 up, and that would be in both denominators. That would be fine. Okay, so yeah, u is the square root of x, just by our very, very first substitution. Hey, we made it. Quite a journey. But yeah, that was really cool. I like that one. Hopefully you did too.